Welcome back, everyone, to this 9th episode for dynamic assignment in Visum or mesoscopic modeling. The agenda for today would be to look at some overview of use cases for simulation-based assignment, methodology behind the simulation-based assignment in Visum, an example setup in Visum, and then evaluation of results or some tips with simulation-based assignment. All right, overview of use cases. Typically, simulation-based assignments would be used for modeling of heavily congested urban or interurban networks where oversaturation and queuing to adjacent roads is present over large parts of the network at different times. So if you have a lot of congestion where there's queue spillback and so forth, particularly in some corridors, you may want to use mesoscopic or dynamic assignment, which models the queue spillbacks in those specific corridors or focus areas. Then modeling of networks with transient congestion effects. Let's say you have work zones and so forth where certain times of day might present different congestion than typical. You can model that with using time varying attributes with the dynamic assignment. Then if you have, again, speeds or tolls that vary by time of day, you can also model that with dynamic assignment or simulation-based dynamic assignment. And then if you have incidents and temporary closures that you want to model the impacts for, you can model such scenarios, and the overall network robustness or reliability and such, or management strategies for that can be evaluated by using simulation-based assignment. Finally, if you have evacuation plans, for example, hurricane evacuation and such modeling, that you would like to see the evacuation time in case of such adverse events, you can use simulation-based assignment as a support tool for estimating evacuation times in such emergency scenarios. All right, now let's get to the assignment method or the basic principles behind simulation-based assignment. Generally, the simulation-based dynamic assignment involves this kind of sequence or step of calculations. So for each assignment interval, let's say it's divided into 15-minute time intervals, we search for paths based on generalized cost in the network. And generalized cost is your combined cost for tolls and so forth with time. Then for each new path that is searched, we redistribute those flows or the OD demand on those different paths or routes in the network. Once the weights for each of those routes or flow is determined, then a simulation is performed on those apportioned route flows. And then once the simulation is done, it produces a new generalized cost in the network, which is basically the experienced simulated travel time for each of the paths. Then this path flows are tested for convergence. If the solution has not converged, it's sent back into, again, searching for new paths or routes in the network. And then the same process of redistribution of flows is carried out iteratively till some convergence criteria is achieved. And once that's achieved, we go to the end of the simulation. Speaking about convergence, we are looking at a dynamic equilibrium assignment in this case. So for each analysis time interval, travelers won't improve their travel times by selecting another alternate route. So this is the same wardrobe principle that applies as in the case of static assignments. It's just that it is extended to the different time intervals that are being modeled in this case. Again, the generalized costs of all routes of an OD relation or an OD pair will typically be quite close when you're about converged in a traffic assignment. And this applies in case of simulation-based assignment as well. Again, this then extends to each time interval that's evaluated. So the general idea of equilibrium is not different from the static assignments. It's just that it's extended further in the time dimensions. For convergence, we use a gap measure. And how is this gap measure calculated? It's by using the vehicle impedance at accumulated values and the current shortest path impedance and weighted by the volumes. Typical gaps achieved are 0.03. So you will see that the gaps achieved in dynamic assignment are usually a little bit higher in value than the static assignment because we simulate whole vehicles in dynamic assignment and those shifts inherently produce gaps that are a little bit higher. So you won't have typically the 10 to minus 5 type gaps that you see in the static assignments. The other termination criteria, of course, is if the gap is not met, then maximum number of iterations is specified. And once those are reached, the iterative loop is closed. For the calculation of impedance of paths or the generalized cost of paths, we have the same sort of definition that we use for the static assignment case, where we specify a linear combination of various attributes or a weighted linear combination. And this could be composed of the travel time, the length of the path, the toll with its respective weights. In addition to the static calculation or static definition for speeds and such in the dynamic assignment, it's also possible to specify within Visum time varying attributes. So let's say you have a school zone or something of that nature which experiences a different speed limit in a given time block. Then you can actually have a time varying attribute associated with speed and have that time of day variation modeled inside Visum using this time varying attribute setup so that during that particular time period, the value of speed or posted speed would be 20 miles per hour, which otherwise would be something like 35 or 40 miles per hour. Now, when we calculate travel time in the dynamic assignment case, what we are talking about is simulated or experienced time, which means that once the paths are found, calculating the time-dependent shortest paths, the vehicles are loaded onto those paths, and then the eventual travel time is reported as the experienced travel time by the vehicle after it ends its journey to the destination. These travel times are measured in short-term intervals. So, for example, you can set the eventual intervals as 7.5 minutes, and that's used as kind of a way to have points of time in which these average travel times are considered for the time interval. Then these are also measured for links separated by turning directions. So a whole movement is typically considered in this case instead of simply the link-to-link travel times and such. This sort of a TTF or travel time function is used in the calculation of the shortest path. So this gives you the time-dependent shortest path and then the experienced travel time and so forth using the FIFO queuing method. With simulation, we have a simulation-based network loading. What this is in Visum is basically an event-based mesoscopic simulation that uses a simplified car following model. There's a lane selection model, and then the intersections are modeled using gap acceptance and signalization is also taken into account if it's coded in the intersection. Let's look at the car following model that's used, or the simplified car following model. It has 3 parameters, and these are the free flow speed, or this could be the posted speed on your link, then the standstill distance, and then the effective reaction time, or reaction time in the car following model. So this basically results in evaluation of 2 states during the simulation. When vehicles are traveling in their free driving state, when they try to achieve basically the free flow speed, and then in the following mode, where the following distance and such is based on this car following model, a simplified car following model, which depends on the reaction time and standstill distance specified in the simulation-based assignment parameters. This is applied to each transport system, so you can have this model separately for trucks, cars, and such. Let's look at some of the properties of the car following model. Now, since we are simulating in this case, then the capacity is not an input for the assignment. So typically with the static assignment, you would put capacity calculation as the input. However, the capacity with the simulation is actually an output. And this is calculated as a function of the reaction time and the effective vehicle length or standstill distance parameters that you specify. So this is more of a dynamic phenomena in simulation-based assignment rather than a static shadow price type mechanism that you see in the static assignments. Then there's also a lane selection model. Within this lane selection model, the simplified form of the lane selection model essentially takes when the lane selection occurs only when first entering a link. So when there's a link-to-link transition for the vehicle, a vehicle can only select a lane in the next link, which can be reached without the need to change lanes. Let's take a look at this example over here with this diagram. So if you look at the approach on the west, the vehicles which turn right can select only the right lane. The vehicles that turn left can select only the left lane. And then vehicles that want to go straight, since all of the lanes are allocated to the through movement, can select any lane from the upstream link. So this is the general way of the lane selection model in the simulation-based assignment. Within a certain link, lane changes don't occur with this event-based model. Next, we have the intersection control. So one of the characteristics of the simulation-based assignment is also that we model intersection movements explicitly, and then opposing flows are also modeled using the gap acceptance and conflicting volumes and so forth more explicitly. If you have signals in the network and you have certain progression factors and time offsets specified for a set of signals that are synchronized, then you can enter time offsets with the simulation-based assignments to capture the impact of progression more explicitly in the simulation-based assignment. With gap acceptance, we model the conflicts and time gaps and wait times to make turning movements when there is opposing flow of traffic with the simulation-based assignment. So the intersection is modeled at a much more detailed level compared to static assignments where you might have a delay function or volume-dependent turn delay functions, but not explicit opposing flows modeled. With the intersection control, we follow the definition of the HCM for critical gap. So this is the critical headway, which is defined as the minimum time interval in the major street traffic stream that allows intersection entry for one minor street vehicle. Then we also follow the same follow-up gap definition through HCM, which is the time between the departure of one vehicle from the minor street and departure of the next vehicle using the same major street headway. With intersection control types in the simulation-based assignment, we can model the following control types. You can have unknown control type, an uncontrolled intersection, two-way stops or yields, then all-way stops. Then we can also have signalized intersections as well as roundabouts. Depending on the type of intersection control you have, gap acceptance will be modeled, and then default gap parameters in the simulation-based assignment are set based on the HCM. Now for modeling of the SBA, let's take a look at network modeling, intersection modeling, and some parameters for the calibration. For network modeling for SBA, we have to set the same transport systems or thesis, and that's set again for links, turns, and connectors as you would in the static assignment. Then we also have to set number of lanes and free flow speed. Note that since this is a dynamic assignment, the number of lanes or correct input of number of lanes is much more critical in this case because simulation is less forgiving than the static assignment when you evaluate the results for the assignment. Then intersection control is also entered in the network. This can be again signalized, partial stop, always stop, and so forth. Intersection geometries are also explicitly specified. So for example, if you have specific channelization, turn bays, and so forth in the intersection, you would input all of that information on the intersection level. Then the parameters of each transport system are entered through the simulation-based assignment parameters, and these are the reaction time, effective vehicle length, and a maximum wait time before the vehicle forces entry into a gap. The next thing we also need for the simulation-based assignment, which is in addition to what we had with the static assignment, is a peaking profile. So we set up demand time series in this case, and we specify time series for different segments of the assignment that we are assigning to the network. If there are time varying attributes in your network, for example, varying speeds by time of day or a certain period within the overall assignment period experiences a different speed or has different posted speed limits. Let's say also there might be a work zone which results in reduced speeds. You can have all of these coded into the simulation-based assignment as a time varying attribute. Additional inputs in case of the intersection geometry then also contain channelized turns, pocket lanes, roundabouts, and so forth. So here, the turning movement is explicitly modeled, and as a result, it's not length 0, but it follows the parameters that are specified in the leg or lane definition when you modify the intersection. Then within the dynamic assignment parameters, This is for actually loading the network, equilibrating, and so forth. We have the following. First, the termination condition or stopping criteria. Here we have maximum number of iterations or a maximum gap. Since this is a simulation, you'd have a random seed. Then you also have the period of assignment. So let's say you're assigning from a given time period, let's say 6 a.m. to 7:30 a.m. as shown over here. And then the network might require a little bit more time to fully evacuate. You can enter this as an extension time interval so that all of the vehicles that started their trip are able to complete their trip by the end of the simulation. So this will be added then as an additional value to the 7:30 ending time of the simulation. Then you also specify the time interval duration. Over here you can see 10-minute time interval duration has been specified, and that would be the resolution at which the aggregated results will be accumulated on the links, turns, and so forth. So then you can look at 10-minute aggregation results for the entire simulation. Then we have certain criteria that allow you to prune paths. So let's say you want the simulation-based assignment to not search for paths after a certain assignment iteration. You can set the last iteration for that path search. So this saves a little bit of time in doing the time-dependent route searches and so forth. So you can cut it off at, let's say, 30 iterations if you're running 50 iterations. So no more new paths are specified, but the existing path set is equilibrated. Then volume balancing can be done in a couple of ways. You can use either MSA to balance the volumes on the routes, or you can use cost proportional, which is basically a gradient-like method which gives you a little quicker convergence in a lot of cases. Gridlocks in the SBA network can be analyzed using the SBA utilization attribute. So SBA utilization is a measure of congestion that we store after we calculate the simulation-based assignment, and that can be used as a way to troubleshoot gridlocks and bottlenecks. Now, since this simulation-based assignment has a hard capacity in the network, which means that queue spillbacks are explicit, if there are vehicles left over in the network after the assignment time period ends due to gridlocks or congestion and so forth, the simulation-based assignment will give you the explicit warning of X number of vehicles that were left in the network due to gridlock or over congestion. So in this case, you might either want to increase the extension time interval or increase the number of iterations so vehicles can be routed over new paths. All right, that was quite a bit of information over there on the slides. Now let's take a look at what some of those look like within Visum by looking at a simple example of simulation-based assignment. Again, I have our familiar Olympus training model over here. And in this case, what we have done is simply use this model to create a simulation-based assignment over it so that we can show a larger scale implementation of this simulation-based assignment and what issues you might encounter while doing this. Let's take a look at the setup first. Over here, I have the demand and then transport systems. Now, if you remember, we have to specify reaction time and so forth for the car following model. So that is specified using this transport systems, and then you select the transport systems for which you want to specify parameters. Click edit. You can see that we have these default parameters set for the simulation based assignment. If these are different in your case, which might be if you have actually access to the loop detector data and you've calibrated or estimated a speed density relationship, then you can enter those over here. The next part that we need for the simulation-based assignment is also then the demand or peaking profile. To set up a peaking profile, we go for demand data. Over here, you can see that we have demand time series attached to each demand segment. So over here, we have, let's say, SOV. You can see that a demand time series named 3 SBA SOV is allocated over here. This is using matrix number 248. And then this demand time series over here is attached to a standard time series. And the standard time series over here is what actually has the peaking profile. So here, number 3 SOV SBA has a time period going from 3 p.m. to 7 p.m. And if I click edit over here, this is specified through adding weights to each of these hours. This you can modify and edit as you need. So you can change the weights over here to specify a given peaking profile that's applied to an aggregate metrics for the entire time period. In this case, this is 3 p.m. to 7 p.m. And this can be specified for each of these different market segments. Now, this is a time series by percentage, which basically applies a peaking profile that across the board applies the same peaking factors in the matrices. Sometimes you have matrices which are available for different time periods at a greater resolution and with uneven peaking included in them. In such a case, you can use actually a time series by matrix numbers. So to create one of those, you can go for create and then give it this name. And instead of time series by percentage, you can select matrix time series and then select and edit. Now here you can specify the different time periods. So here I'm just going to go from start time, let's say again 1500 to 19 in 1 hour duration. Now here you can see that there's no weight specified. So what we do over here is instead of having a weight, we specify an actual trip table. Some regions may have actually a trip table that is built up from, let's say, an activity-based model and such, in which case you can aggregate the trip table up to that time of day and time slice, and then assign that specific trip table to this matrix reference. This way, you'll have a time series that explicitly takes a matrix into account and models the uneven peaking and such that might be occurring in your network. In the example that we have over here, we've used a more simple concept of peaking profile. And we've given this peaking profile to a time period matrix from the PM time period. So over here in the demand segments, then we have the assignment trip table specified, and these are all PM trips for the different market segments. And we'll be applying the corresponding time series or weights defined for the different time periods and market segments. So this is just the additional setup that's needed for the simulation-based assignment in Visum. Once you have this basic setup, you're actually already ready to run the simulation-based assignment. Over here in the procedure sequence, right at the end, we've created a new set of procedures to set up the simulation-based assignment. So first we do some matrix calculations to basically bring in the PM time period matrices into the actual operating matrix for the assignment intervals. Then in PRT assignment, we have essentially the same market segment selected as the static assignment, as you can see. The difference over here is that instead of using the biconjugate Frank-Wolf, which we were using for the static assignment, we use the drop-down and select simulation-based assignment from it. Now, once you select that, you click this and hit edit, you can modify the parameters. And this is kind of what we saw in some of the slides, where you can specify the maximum number of iterations, the gap criteria, and then some more parameters for random seed, gridlock avoidance, and path search limitation, and so forth. Then you can also see over here that we have a use current assignment result as initial solution. This is basically the warm start option. So if you already have a simulation-based assignment calculated and you'd like to use that result as a starting point for a new assignment, then you can check this option and that will become a warm start simulation-based assignment. This might save you runtime in cases where you have only a small difference in the OD matrix, and then largely the assignment remains the same except for new network loading and a few differences in the OD pairs. The assignment time period over here, you can see that this is 1600 to 1900. This would need to match the time period that you have over there. So let's say you had 1500 over there, you would match that 1500 to 1900 over here, and then the time for traversal or the post-assignment time period. Now, how much time to allow for this post-assignment time period can be taken from typically the congested travel time scheme from your static assignment. So let's say you have the maximum value of the congested travel time scheme in the static assignment as 1 hour, which is basically the time it would take to traverse the entire network. That's roughly a starting measure for how long of an extension interval you specify. So once you have that, you can then put 1 hour over there. Over here, if you want to evaluate at more or less the time intervals, then you can change this resolution at which you want to store the results for the link level aggregations. In the assignment that we have run over here as the test, we've saved it at 15-minute intervals. So once you specify these intervals over here, then you click create analysis time intervals for simulation time period. What this does is it creates additional attributes required to store the results of that simulation-based assignment in your network. So this time period should match the time period that you have in the demand time series, and that way it knows to pull the demand from the correct time slice. Then for volume balancing, again, these are equilibration strategies. So you can use either the cost proportional or MSA method for balancing. Like I said, cost proportional is kind of a gradient-like method, so it will typically converge quicker than the MSA. And then the step size control essentially tells the balancing algorithm how much of volume to actually shift in the process of equilibration. So this provides the direction of the move, and then this is going to give you the magnitude of flow shifted. If you are modeling cases where you want a preload in the network, let's say there's some sort of a bus related congestion and things of that nature, or bicycles interfacing with the traffic, you can put a preload on the links. So you can use this base volume checkbox and specify a preload for the transport system and store those preload values in any of these given either user defined attributes or the extra attribute provided in the Visum links. So this is essentially just a check for preloading traffic onto the assignment network. Finally, we have the visualization. So if you record the vehicle trajectories for visualization, what this does is it stores the trajectories generated during the simulation of traffic and then allows you to look at the moving beans or moving dots in the network that might be further useful for just demonstrating the results and also very helpful for picking up gridlock and congestion in the network and troubleshooting the network for congestion and gridlock. If you don't want to have a huge amount of disk space used for those trajectory storage, you can specify how much to restrict the trajectory recording. This way, if you only want to record a corridor for flows, you can restrict the trajectories to only active links by specifying a link filter, and that way only trajectories on the active links will be recorded. You can also constrain the time period in which the trajectories are recorded by checking the from and to and then restrict trajectories to time period. Similarly, you can have temporal resolution for the trajectories based on your own specification. Now, just to give an idea of the runtime, network loading in this 4-hour period takes about 6 minutes for the simulation-based assignment for this entire network. Once we run this simulation-based assignment, we can look at the results as follows over here. So you can look at the growth and decay of volumes on the links like this. And you can see that these are all time varying attributes. And we're looking at the 15-minute resolution. And as you progress in the time period, the flows get greater and greater and the congestion level builds. What we are displaying over here for the heat map or the color is actually the SBA utilization. And these links which are brighter actually show links which are more congested. So these are the congestion areas in this link where there's a high SBA utilization value. And this is kind of the exaggerated values so that we can show you how effectively you can troubleshoot some of these over congested links. Then the strategy is to actually look at some of these links which are quite congested. And then you can select links over here, click on one of these links, and if you right click and look at column charts, you can have a look at the different volumes per time interval, the way the queuing is building up. So you can see that this link, since it's over congested, the queue just builds up and stays quite high throughout the simulation. And then the travel time, or the congested travel time, you can see that it started at free flow and dropped down all the way to the over congested condition. And all of these column charts can be configured to see the attributes that you want by using this settings. And then over here, you can create new column charts and then select the attribute that you want to look at. When you calculate the SBA, some special attributes related to SBA are calculated. So you can look at all of these SBA related attributes by looking at the SBA reaction time factor, queuing, density, and so forth. So these are the additional SBA related calculations that are stored once you run the simulation-based assignment. Now, lastly, the other benefit with the SBA is that you can actually visualize the moving beans in the network, and that you can look at through this view and then SBA visualization. This brings up the SBA visual over here, and this you can play as you would typically in, let's say, a Visum type simulation, which is a playback in this case. So here you can see the moving beans in the network. You can also see areas of congestion which appear in pink. Then if you want to get closer to a certain intersection, you can pan and zoom closer and look at some of these movements more closely. So here you can see that there's some congestion building up at the network nodes. All of these stopped vehicles show up in pink, and that's because the visual is graded by color. And this gives you an idea of the gridlock in the network. Now, in this case, we haven't specified any intersection control. As a result, vehicles have some default behavior. And in this case, since it's an unknown link type or an unknown node type, basically there is no real control on the intersection except for the capacity of the downstream link and so forth. So if you want to look at what's going on over here on this node, you can go back to the network editor and then look at that specific node over here. And if I zoom further in, you can double click this and look at it in the Junction editor. Now, if I look at the links coming in, you'll notice that there is a lane drop over here. So if I look at this link over here, this has 2. And then if I look at this link over here, this might have a lane drop or a difference in geometry that results in a different capacity downstream, which is causing the congestion in this case. So in this case, the congestion is link-based rather than based on the intersection, because at the intersection level, our control type is unknown. Now, if we were to add or edit the geometry over here, we can again go back to the Junction editor, change the control type. Let's say over here we wanted to add a signal, change it to signalized. If we had to edit this geometry, we can change this geometry by giving lane groupings and so forth. And one useful item that we have, or feature we have with the Junction editor, is the signal templates. So let's say you have a repetitive signal template that you want to apply in a lot of your intersections. What you can do is load signal templates, which are stored in this install folder that comes with Visum. In the data, you'll see signal templates for the right-hand traffic.net. This again is the net file that we had discussed earlier in our tutorials. You can drag and drop this over here and then read this additionally into the network. And what this does, it brings up the signal templates. So then let's say you add a signal and you call it stage based and click OK over here. You can then see that we have stage templates that you can use. So if you select this and select the number of stages you want, and then a template, this will give you the stage transition. And then this way, you can take a look at actually the stages. So let's say I have the signal timing view over here, and I look at stage template. I want 2 stages, and this, then you can have stage template and flip through the different templates, and that will let you preview the template. So you can also use this as a quick editing method where you can apply a basic template to a whole bunch of intersections which are signalized, and then go in and tune your signal editing through this template editor. We'll have more information on some of this detail for signal timing and geometry coding also in the next session that we are having, which is based on exporting the mesoscopic simulation from Visum into the more microscopic simulation in Visum. So we will cover the junction details or editing details in more depth in that section. Now let's go back to our PowerPoint for some of the final tips and tricks. So as we talked about the car following parameters, the simplified car following parameters result in this kind of a fundamental diagram. So what you are basically calibrating for is your parameters for this fundamental diagram. So shock wave speed and so forth. So here, the reaction time and the effective vehicle length are the ones that you're tuning for. For the most part, you will end up having a parameter for that reaction time, which would be estimated from, let's say, a speed density diagram derived from a loop detector and so forth, if you do enter some of these parameters on your own. These parameters are applied globally as well as individually on the link. So let's say there are certain subset of links in your network for which you have the data and want to use different parameters. You can then go specifically to the links and have an override set over here for the reaction time factor and the vehicle length factor. And that way, these parameters would be adapted for that particular link. Let's see how some of these parameters actually impact the results. So here we have, for example, car following parameters for the basic vehicle length and speed. So this is what your car following looks like when you have your basic parameters set. Then let's say you change the reaction time. How would the car following model take effect then? So over here you can see that if we have a 1.2 second reaction time versus 2.4, the one in the first case discharges much quicker than the other because following is a lot more closer or the reaction time is quicker. Then if we change the standstill distance or the gap between vehicles when it's a traffic jam, you can see that that headway is maintained is greater if we specify 5 meters versus 2 meters. Then we can also see the effect of speed. let's say we have 50 versus 80 kilometers per hour, you can see that the higher speed discharges quicker. So these are the subtle ways in which your car following model parameters will have an impact on the simulation and the discharge time for the queues and so forth. Now, gap times also can be edited in the junction editor by using the SBA related properties over here. So let's say on certain turns you wanted to change these parameters from the defaults, you can specify these overrides and such in the junction editor for the turns. The general gap acceptance parameter for the calibration is taken like this, with the conflicting flow versus the potential capacity. Then some useful hints. What is not used in simulation-based assignment? And how do you see which attributes don't play a role? Then conflict between lane turns. So what is not used in simulation-based assignment? We don't use volume delay functions. We don't use explicit capacities or the T naught or base delay applied to the turn or nodes. Then we also don't use MPA proportions specified in the traffic assignment on the connectors. So you can have multiple connectors, but you can't specify explicitly the proportions or shares in that case. The irrelevant network objects that don't take effect in SBA assignment are typically hatched out like this. So you will know what parameters not to look at when you look at SBA results. With the intersection control and right of way, again, you can incrementally add junction control in the SBA, so you can keep a free flow intersection and then fine tune your junction to add new terms in it. Once the SBA is done, what are the outputs and evaluation that come out of it? Of course, you have the assignment results that we knew. You can also get select link calculations and skims. So here, the skims and select link calculations in the SBA are actually time varying. So for example, if I went over here for the flow bundles, if I look at a select link calculation with SBA, you'll see that in addition to the market segments, you can apply temporal restrictions. So the same static assignment type results are available with the SBA, but in addition, you can have also temporal restrictions because this is a dynamic assignment.